Hello AP Stats students, this is 7.1 on sampling distributions. You're going to notice in this chapter that we've been doing sampling distributions this whole school year, and hopefully you put that together. So we've used these words before, but we haven't really defined them that much for you. A parameter is a number that describes some characteristic of the population. In statistical practice, the value of a parameter is usually not known because we cannot examine the entire population. So let me skip down to this table and then we'll come back up. So if we want to know the parameter, the population proportion, we call that P. If we want to know the population mean, we call that mu. And if we want to call the population standard deviation, that's sigma. A statistic is a number that describes some characteristic of a sample. The value of a statistic can be computed directly from the sample data. So, if we're getting it from a sample, the sample proportion is p hat. The sample mean is x bar, and the sample standard deviation is s. We've been using these symbols the whole time, and I've been pretty careful with them, but you probably haven't noticed. So in these two, identify the population, the parameter, the sample, and the statistic. So the Gallup poll asked a random sample of 515 U.S. adults whether or not they believe in ghosts. Of the respondents, 160 said yes. So the population is all U.S. adults. And we have no idea what all U.S. adults are going to say. This is a proportion, so we're looking for P. The proportion of all U.S. adults who believe in ghosts is not known, but we do have the sample, P hat. The sample proportion, P hat, of U.S. adults that believe in ghosts is 160 out of 515. So the sample is that 515 U.S. adults, and the statistics P hat. During the winter months, the temperature outside the Starnes' cabin in Colorado can stay well below freezing, which is 32 degrees Fahrenheit or 0 degrees Celsius, for weeks at a time. To prevent pipes from freezing, Mrs. Starnes set the thermostat at 50 degrees Fahrenheit. She wants to know how low the temperature actually gets in the cabin. A digital thermometer records the indoor temperature at 20 randomly chosen times during a given day. The minimum reading is 38 degrees Fahrenheit. So we're looking for the population. This is kind of a weird one that we'll never actually use. The parameter is the overall minimum temperature. The statistic is that 38 degrees Fahrenheit, which is the minimum reading from those 20 randomly chosen times. So this is the sample. Those 20 randomly chosen readings are the sample, but the minimum temperature overall is the population. So it may be lower, we don't know. Mr. Donahue wants to estimate how much time students studied for exams. To find out, he surveyed a random sample of 10 students and asked them how many total hours they spent studying outside of the school day for their midterms. From this sample, he found the average amount of time spent studying to be 6.2 hours. Unbeknownst to him, Mr. Amstutz was wondering the same thing and asked a different random sample of 10 students and found the average amount of time spent studying to be 5.6 hours. Why didn't the samples have the same mean? Well, they asked different people. Either one of them took a better sample, but if you're asking different people, you're going to get a little bit of variability, so that's what we call sampling variability. So now imagine that Mr. Amstutz and Mr. Donahue take every possible sample of 10 students from the building and found the mean hours studying for the midterm exams. This is called a sampling distribution. So every possible sample of 10 students is the sampling distribution. This is a theoretical thing. We don't just take sampling distributions, we don't just make it. There are some theories that are built up that help us estimate it. But we can do these simulations and create estimated sampling distributions. So we use Fathom software to simulate choosing 500 simple random samples of size n equals 20 from a population of 200 chips, 100 red and 100 blue. 7.2 is a dot plot of the values. P hat, the sample proportion of red chips from these 500 samples. Is this a sampling distribution? Well, no, it is not every possible sample of size 20, but this is going to be a nice estimate of the theoretical sampling distribution. So if we're going to describe this, then we're going to say all of our socks. So the shape is bell-shaped and symmetric. It is also single-peaked. It doesn't look like there's any sort of outliers or unusual characteristics. The center is about at 0.5, and the spread is from 0.15 down here to 0.8. Suppose your teacher prepares a bag with 200 chips and claims that half of them are red. A classmate takes a simple random sample of 20 chips, and 17 of them are red. So 17 out of 20 are red. This is our p hat. This is our sample proportion. What would you conclude about the teacher's claims? So 17 out of 20 is 0.85. So 0.85 is out here. Now, if I was not lying, 0.85 would be an outrageous coincidence that I would get 17 red chips. Because I would likely get about 10 red chips, right? Because 10 would be right here in the middle. So what could I conclude about their claim? The claim is probably wrong. I probably lied about half of them being red. There's probably many more that are red that would make this more likely to happen. A statistic used to estimate a parameter is an unbiased estimator if the mean of its sampling distribution equals the true value of the parameter being estimated. Means and proportions are typically unbiased estimators. So would the sample range be a biased or unbiased estimator? So basically, it's a good estimator if we take the mean of our sampling distribution and then it's close to what's actually possible. So if we look back at our last one, the mean of our sampling distribution is about 0.5. Well, half of them are red, then that mean is 0.5, which is equal to half of those red chips. So this mean of these p hats is equal to the population proportion p of 0.5. So in notation, mean of x bar is roughly equal to mu, right? The mean of my sampling distribution is equal to my population mean, or for proportions, the mean of my sample proportions is roughly equal to my population proportion. So if we think about sample ranges, well, sample ranges are usually going to be smaller because you're not going to have the highest and the lowest in a sample. So this is not going to be an unbiased estimator. It's going to be a biased estimator because it's always going to be smaller than the population. Which of the following distributions do you think best estimates the population mean? Well, they all are centered around the same thing. However, in this last one, I'm a lot more confident that my middle estimates the population mean right there at about 6.0 because it's closer together. So each of these histograms is a simulation of taking samples from the same population and measuring the sample mean. Each of these used a different sample size. So this goes back to our running example. As we increased our sample size, our spread or standard deviation was smaller. So this would be a larger sample size. And this would be a smaller sample size. So why is sample size important? Well, the larger the sample size, the more confident we are in our answer because we're a lot closer to the true population, either proportion or mean.